In today's functional analysis class, we discuss about basis of a Banach space, and we are thinking about a number of elements of the basis of a Banach space. So we prove a theorem. So this is the theorem. It is theorem 8.4 in your text. A Banach space cannot have a denumerable basis, or it cannot have a Hamel basis. Proof. Suppose that the Banach space have a denumerable basis. Suppose that a Banach space X has a denumerable basis x1, x2, x3, etc., xn, etc. For m equal to 1, 2, etc., let ym equal to span of x1, x2, etc., xm. So you know that ym is finite dimensional. So being finite dimensional, it is closed in X. Being a finite dimensional space, being a finite dimensional space, ym is closed in X. Therefore, the complement dm of ym is open in X. So dm is ym complement and ym is closed. And since ym is spanned by x1, x2, etc., xm, xm plus 1 does not belongs to ym. Since xm plus 1 does not belong to ym, we see that ym is not equal to x. Therefore, by 5.6c, ym interior equal to empty is 5. Therefore, ym complement is dense in X. That is, dm is dense in X. So you know Bayes' theorem. So Bayes' theorem is, if X is complete, the intersection of countable number of dense open subsets of X is dense in X. So this is Bayes' theorem. So using Bayes' theorem, we can see that since X is complete, being a Banach space, since X is complete, using Bayes' theorem, intersection m equal to 1 to infinity dm is dense in X. But you know that as m tends to infinity, dm is equal to mt, because the span of x1, x2, etc., xn, etc. is x. But span of x1, x2, etc., xn, etc. equal to x, since it is a denumerable basis for x. So this implies intersection m equal to 1 to infinity dm is empty, which is a contradiction to the fact that intersection m is equal to 1 to infinity dm is dense in X, which is a contradiction. Therefore, our assumption is wrong. Therefore, a Banach space cannot have a denumerable basis. Therefore, we can observe that the basis of a Banach space is either finite or it is uncountable. Result note: the above theorem shows that a Banach space X is either finite dimensional or else it has a basis which is uncountable. So we can write one more remark. An infinite dimensional separable Banach space has a basis which is in one-to-one correspondence with set of all real numbers. So an infinite dimensional separable Banach space has a basis which is in one-to-one correspondence with the set of all real numbers. Thus, from the viewpoint of constructive analysis, the concept of a Hamel basis is not suitable for an infinite dimensional Banach space. Now we have some concepts. We define shorter basis. Let X be a normed space. A countable subset x1, x2, etc. of X is called a shorter basis for X if norm xn equal to 1 for each n, and if for every x in X there are unique k1, k2, etc. in K such that X is equal to sigma over n kn xn. So if X is finite dimensional and x1, x2, etc. xm is a Hamel basis for X, then x1 by norm x1, etc. xm by norm xm is a shorter basis for X. For example, if ej equal to 0, etc. 0, 1, 0, etc. 0, where 1 occurs only at the jth place, then e1, e2, etc. en is a shorter basis for kn, and it is called the standard basis for kn. Also, if ej is 0, etc. 0, 1, 0, 0, etc., where 1 occurs only at the jth place, j is equal to 1, 2, etc., then the set e1, e2, etc. is a shorter basis for C0 not for LP as well as for C0 for 1 less than or equal to P less than infinity. It will be called the standard shorter basis. Now, if x1, x2, etc. is a shorter basis for X, then for n equal to 1, 2, etc., we define fn from x to k by fn of x is equal to an for x is equal to sigma n equal to 1 to infinity an xn, and this belongs to X. The uniqueness condition in the definition of shorter basis shows that Fn is well defined and linear on X. It is called the nth coefficient functional on X, corresponding to the shorter basis x1, x2, etc. for X. If X is finite dimensional, then by 5.4b, each Fn is a continuous linear functional. That's all for the day, and this completes Unit 1 of functional analysis.